Howdy, folks. So, today we're starting on thermochemistry and about energy. And so this is going to be broken down into a lot of different smaller videos, mainly because these subjects do easily break down into small little sections. This first video is going to be more about the theory, how we think about thermochemistry, which is going to in turn express how we deal with thermochemistry in the long run. So let's go ahead and get started. This quote, I usually don't talk about what's on the first slide, but this quote was told by one of my professors when I was an undergraduate. Very great man. I miss him. But he was taught thermochemistry. He taught general chemistry. He taught a lot of different, very advanced classes. But real character. Talking about chemistry. You don't want the explosions essentially following you down the hall. You gotta be a little careful. But okay. Now, thermochemistry is, of course, the study of energy and heat within the core of chemical reactions. But what physically is energy? Energy is the ability to transfer heat or to do work. So be able to transfer heat, so something warms up, something cools down. That's because energy is being transferred. But things don't have to warm up. Work can be done instead. Work, in terms, is typically discussed as a force applied over a distance. And this force being typically mechanical in nature. So, for example, a hot object can be brought close to a balloon, and that thermal energy can transfer into the balloon, and the balloon can expand at a constant temperature. And it can expand. While the balloon expands, it is performing work. So, typically we use work in terms of a piston going up and down, because that's how we use that in the majority of our engines. Now, while physics will deal largely with mechanical energy, chemistry will not. We'll look at a little bit of it, but most of it will be left to the realm of physics. But the few types of energy that could come up, the realm of physics will be covered in this slide. Kinetic energy is one. It's the energy of motion. We won't usually deal with this because the scale of atomic motion is too small to be of large account. But all atoms have kinetic energy because all atoms are technically moving on a molecular level. All electrons have energy, kinetic energy, because they're all spinning around the nucleus. However, since kinetic energy is 1/2 mass times velocity squared, even if these atoms are moving really fast, they have incredibly small mass, so the kinetic energy never really accounts for a whole lot. Potential energy is a way of considering stored energy. Is energy dependent on position? We sometimes talk about chemical energy as being potential energy. Essentially, you could think of a bond as potential energy. Typically, in physics, when you think of potential energy, you think of, well, there's a rock on the top of a hill. Because it's high up, if it were to take a tumble, it would roll to the bottom of the hill, transferring its potential energy into kinetic energy. But in terms of atoms and molecules, chemical bonds are potential energies. Once you start breaking bonds, that's where you give the initial push to the rock, then they start making bonds, and the rock starts to roll down and you're releasing energy. But bonds are a form of potential energy. However, this could be other things. You could be a spring, compressed, ready to go. A piston locked in place, unable to expand. There's a very variety of ways you can keep potential energy stationary until ready. Other types of energy is the main other type one is electrical energy. Electrical energy is the energy we get by transferring electrons over from one place to another. I think it's over a potential gap, but either way, we won't deal with that this semester. Next semester, if you're looking at batteries, we will be harnessing that electrical energy. But here we are going to treat these guys as if they had none. Now, while the main unit of energy we will use is a joule, which is the SI, the System International unit, we also have the units that you're probably more familiar with, which are calories. And we can have both little c calories and big C calories. Big C calories is essentially a kilocalorie, 1,000 calories. But a calorie has a very specific definition. 1 calorie is the energy it takes to heat up 1 gram of water by 1 degree C. One of the rules that we will not discuss in this chapter, but rules that we'll go into later, is that this is like almost a programming language. If A equals B and B equals C, then A must equal C. Repeat that again. If A equals B and B equals C, then A must equal C. So a lot of times when we're measuring the energy of a reaction, we can measure the energy one way and then compare that to the energy gained or lost by water. And we can make a direct relation between the two, where we're saying if the A is equal to this and C is equal to this and these are the same numbers, then this is the same energy. But there's an easy way to convert calories into joules, but joules is actually an SI unit that is a function of work and distance, and work being a force is a kilogram meter per second squared, and then a distance makes it meters squared. But we're going to just use the unit joule. You don't have to know this conversion down here, but it can be of use. One of the biggest and hardest things to consider here is now we need to really closely think about what is going on. We need to classify things as what we call the system and the surroundings. We need to think of our problem and encapsulate what is going on in there. So when we talk about a system, it is the place where we are wishing to study something, usually a reaction. So it's not always the place where the energy is produced, but it is the place we are wishing to study. Now, in the case of chemical reaction, the reaction is usually the system. So if I want to study this chemical reaction, the system is the mixing of those molecules. The surroundings, by definition, is everything around the system. So I have a basically a Venn diagram where the universe is everything. The surroundings and the system are within that scope of the universe, and the system is whatever the surroundings are not. And now, depending on how we are considering this, we can scale up the system to be as big or as small as we wish. If I'm studying the human body and its chemical reactions, the whole body is a system. If I'm talking about digestion, I can just say, well, the digestive tract of the human body. If I'm talking about, well, the digestion only in the mouth, then we can break it down into just the mouth. You can break it down smaller and smaller and smaller, however you wish to do. I can talk about the energy flow into the building I'm in. I can talk about it into the room I'm in, or just the body that inhabits the room in the building. I could talk about the system being the town I'm in, scaling it much further, the state. Though typically we will keep the system to be relatively small because you want it to be well defined and easy to study. If I'm talking about the state, it's going to be really hard to study the whole state. If I'm talking about the town, still very difficult. Might be a lot easier to do the building, even easier to control the room, a lot easier to study just the body inside the room. But the flexibility is that we will be able to classify what is the system, what is the surroundings. Now, a system can be considered open, closed, or isolated. And what does that mean? Is that a system can be something that can where matter can transfer out of, as well as heat. It could be a sealed container that can only transfer heat, or it could be an perfectly sealed and isolated container that can either transfer heat or matter. Now, so for example, an open container would be like a coffee mug without a lid. It releases heat out the top, but you can also drink out of the top. Now, a closed system would be like a Tupperware container. If you heat it up or cool it down, the Tupperware can transfer heat into it, but none of the food can go into or out of it. Only heat can be transferred. A perfectly isolated system would be like a thermally insulated thermos. You put hot coffee in there, you close the lid, and it stays hot all day because heat is having difficulty transferring out of the thermos. So, depending on how we put the system, we can have heat or matter transferring at any given time. But so, now that we have the concept of system and surroundings, we need to talk about the two major types of energy that are going to be transferring to and from the system. So we're going to talk about heat. Heat we're going to reference with the small letter Q. Very important, small letter Q. And the small letter W for work. The idea that heat can either come into the system or out of the system. These values of energy exchange are rates. They are rates of energy change, and that we're looking and comparing before and after situations. And so, depending on how the transfer goes, you could get a positive Q or a negative Q. Positive Q suggests that the final amount of heat in the system is higher than the initial amount of heat. Something has warmed up. The heat has increased. If I go outside and go for a jog and this late June, early July weather and come back, I will be very heated. I will have warmed up. I will have absorbed heat, both from the sun and the air and the exercise. Negative Q suggests that the final heat is less than the initial Q. We have lost heat. And it's not really lost heat, is that heat has been transferred somewhere else. When something has absorbed the heat. Here's what's very important. When the system gains heat, it gains it from the surroundings. The outside is coming in. If I lose heat, it is going from the system to surroundings. So in this case, if I run around outside is the surroundings, my body is absorbing heat from the surroundings. If I go and step into a walk-in fridge, I will cool down, because the surroundings in this case is the walk-in freezer or fridge, and it absorbs my heat. Now we call them by the Latin terms endothermic and exothermic. Endo meaning into, heat is flowing into, and exo meaning heat is exiting the system. Now the same thing can be said about work. Work can be done on the system by the surroundings, or work can be done by the system on the surroundings. So it all depends on what's going on. What is your system and what is your surroundings? If there is a building collapse and I am applying and I'm picking up rubble, if I am the system, I'm doing work on the surroundings. Now, if there's a building collapse and I am under the rubble, the surroundings of that building is now doing work on me. It is pressing me down and crushing me. Where this is typically going to be the case is whether a balloon is expanding or contracting. Whether a piston is expanding or contracting. A balloon, being the system, will expand until the external pressure and the internal pressure are the same. So if you push down on the balloon from outside, the balloon will shrink, be compressed. The balloon will push back, and so depending on whether the balloon is expanding or contracting depends on whether the work is being done on the balloon or by the balloon. Now, so the first law of thermodynamics. We skip the 0th law, that'll be for upper level chemistry, but that's the A equals B equals C. But the first law deals with our system and surroundings. The first law is the law of conservation of energy. That energy can neither be created nor destroyed. The energy does not magically appear and does not magically disappear. It can only be transferred from one form to another. So, whenever we produce energy, it had to come from somewhere. Whenever we lose energy, it is going somewhere. That's part of why a lot of great things don't work. That the idea is that any energy lost by the system has to go to the surroundings. Every energy gained by the system has to come from the surroundings. This is why we cannot simply open up our car doors with AC blasting and cool off the world. Air conditioning converts energy into cooler air. However, that cooler air gets cooler by taking the heat from our hot air and throwing it outside. So we're spending energy to separate cold from hot. Normally, things meet in the middle. You put a hot thing and a cold thing together, you get two tepid things. You pour a bunch of ice into a hot, steaming hot bath, you get lukewarm bath water. So, in order to separate things, to freeze those ice cubes back out and get steaming hot bath water again, it takes energy. And in order to do that, it's separating the hot from the cold and leaving the cold in the car. Well, if you were to open the windows and let the cold air flow out, it's going to re-meet with your hot air, and you get tepid air again. And you've just burned energy to do nothing. So that won't work. Energy has to come from somewhere. We'll discuss this more in nuclear energy. Energy seems to come from somewhere, but really it's coming from the destruction of a small amount of mass in the form of our equation E equals mc squared. Nuclear energy breaks down a little bit of mass and converts that to energy. That's how nuclear energy produces so much. But the idea is that energy must be conserved. The heat lost by the system must equal the heat gained by the surroundings, and vice versa. When we consider this, we will consider internal energy. We'll use the letter capital U. Capital U, the internal energy of a system, is just the sum of all energy types of the system. Now, we do not care about absolute energy. There's only very few things we'll care about absolute in this chapter. Absolute means the energy right now at that given point. Let's say, how much energy is there right now? That has no meaning for us, and it's almost impossible, if not is impossible, to determine. What we will in turn study instead is the change. We will use the Greek letter delta. That's that capital triangle, delta U. That stands for the change, the difference in energy. So we will look at how much energy was stored in there initially and how much energy is there now. So the difference in that is the change in internal energy. So forget the fact that it's hot outside. If I go for a run, a jog, I have expended some amount of my energy. With that in mind, the amount of energy I started with minus the subtracted from the amount of energy I have finally is the energy I have lost in terms of calories. So we can calculate that. We don't necessarily know where I started at, whether it was 500, 5 million, 5 billion calories. But I know afterwards it's whatever I started with, say 5 billion, but 100 less than 5 billion. All I know is that, I expended 100 calories because I'm 100 calories less than whatever I started with. And that can be directly determined, but the initial amount could not be. So we will use the delta very often. Delta means change. Greek letter delta, which is our triangle, means change or difference. As I said, there are two main types of energy, our work and our heat. We will largely ignore the kinetic energy. We'll largely ignore the potential and the electrical energy. So we only really deal with work and heat. Really, that's all we need. That's what we need to run a good engine. Unless we're running an electric vehicle, we need just work and heat. So when we combust gasoline, you're taking a chemical, applying a spark to ignite it, and what is happening is it is turning into gas and expanding in a piston. This gas will expand the pistons and by process produce work. Now, due to the clever design of the engine, when we have to recompress the piston to get it back in order, it uses less energy work than it generated. So it doesn't waste a lot of work when it recompresses it. As recompressing it, it's pushing out the old gas and inserting the new gasoline. However, we also produce heat. The gas doesn't expand cold, it expands and heats up in the process. And so we lose some amount of heat as it's coming out of the tailpipe. If you ever felt the tailpipe of the vehicle or stood behind your car while it's running for any period of time, your legs get mighty hot, if not start to burn, because of the heat energy being lost out of the tailpipe. This is also partially why vehicles are poorly efficient. We lose a lot of energy and heat. Whenever we lose energy as heat, we're wasting energy. So work, as I said, is force times the distance. It can be Newton times a meter, or kilogram meter per second squared times a meter, but it's a force applied by a distance. If the force doesn't move the object, no work gets done. So it doesn't matter how strong a force, if no distance is moved, no work is actually done. So I could heat up a container filled with gas, but if that gas container isn't allowed to expand, it's not going to do any work. You just pressurize the gas in the container. Like if I let a soda sit out in the sun and that soda warms up, it'll start to pressurize. However, if you don't open it, no work is going to be done. It will eventually cool back down, the heat will be lost, and it get back to its original starting point. But so long as it doesn't explode and it's not opened, no work actually gets done. But as soon as you open the soda, work is allowed to be done because the gases are allowed to expand. Now, heat, as I said, is by definition transferred from hot to cold. A cold object absorbs heat until both are at the same temperature. If the system is hotter, then the surroundings will gain that heat. If the system is colder, the surroundings will give the heat. So depending on object temperature, heat will always flow from hot to cold. It's only in very special cases like refrigerators and air conditioning that we can force it against that way by compressing a gas and then allowing it to expand, and then it cools down. Okay, so let's put this all together. And when we talk about internal energy of a system, we can talk about this as equal to the total amount of heat flow and the work flux on a system. So if a particular engine absorbs 58 joules of heat and produces 70 joules of work, how's the internal energy of that system? So real quick, this is not very much. Delta U equals Q plus W. It says it absorbs 50 joules, 50 or 58? 58 joules of heat. So absorbs means increases. Now we say the work, it produces 70 joules of energy. Produces means the energy is leaving. So our internal energy in terms are 58 joules minus 70 joules. The total change is negative 12 joules. joules. Just like that. The hardest part on a problem like this is just thinking about what are the signs, what are the relative signs. Now, we have one or two more things before we stop this video. The last major topic is state function. A state function is a special type of function in that in a state function, the path to get from point A to point B does not matter. The energy produced by a state function is independent of the route. Independent of the route of which you get there. Now, what does that mean? It means it doesn't matter whether it doesn't matter how you walk a path, whether you take the straightest path or you take the path that avoids all the traffic, that's most economical, you still get the same energy. And this is kind of hard. A lot of things we do are directly path dependent. If I walk from point A to point B, the straightest line takes the least amount of time. If I try to walk just the edges of the triangle rather than the hypotenuse, it's going to take longer. But in a state function, that does not matter. Basically, I can make a reaction take one step. I can break this reaction down into 2 steps. I can break a reaction down into 5 steps, 15 steps. If the net change is from point A to point B, it doesn't matter how many steps you break this down into it, the energy is always the same in a state function. We only look at the starting point and the ending point and the direct change. This is not true about path functions. Path functions, as I said, are, or path-dependent functions, like distance travel. That's also true for work and heat. The energy stored in gasoline is constant. You don't get more energy or less energy in gasoline depending on how you burn it. The energy is the same. However, depending on how you burn it depends on how much heat and work you can get. The same octane gasoline put in 2 different engines from 2 different cars with 2 different fuel efficiencies can give you 2 different amounts of heat and work. But note that the sum of those 2 things together must always add up to the same function. That's because the internal energy is a state function and it will not change. So the more fuel efficient the car it is, the less heat you're losing and the more work you're gaining. But as work goes up, heat must go down. As heat goes up, work must go down. That is why it's so important to avoid heat loss wherever we can. Because once we lose heat, you get less work. Work is what we want to make things happen. This is very important. This is very important. This is how engines work. This is why there's less heat loss in a diesel engine, and so you get a greater fuel efficiency out of a diesel engine. So even though diesel gasoline costs more per gallon, it has a higher internal energy and you get less heat loss, so you get more mileage, which is another reason why we get more power. That's why we usually use diesel in heavy trucks. And so all state functions, when they are represented by capital letters. We will look at internal energy, delta U, and enthalpy, delta H, this semester. Second semester, you will look at Gibbs free energy, delta G, and entropy, delta S. Those guys are also state functions. So this idea here is that a path function changes the amount of energy you can get. So imagine these two scenarios. I'm not going to do a lot of the math, but scenario 1, they both involve a piston expanding from 1 liter to 2 liters. No matter what. Scenario 1, the piston directly expands from 1 liter to 2 liters under a constant external pressure of 5 bars. So, work is a force, in this case a pressure of 5 bars, times a change in distance. In this case, we have to worry about a change in volume. So work is equal to negative pressure times the change in volume. Here's a little conversion factor. So in scenario 1, it changes by 1 liter in volume under external pressure of 5 bars. So we get 500 joules worth of work. In scenario 2, we break down the expansion into 2 steps. The first expansion is 1 liter to 1.5 liter under a pressure of 7 bars. And then one of the masses is removed and we're allowing it to continue to expand to under the pressure of 5 bars. So we break it down, the work total is the 2 different expansions. So under 7 bars, it expands by a half a liter. And under 5 bars, it expands under half a liter. So the first energy is negative 350, the second negative 250, and so you get negative 600 joules. By breaking it down into 2 expansions rather than 1, you get more energy. And the smaller and smaller and smaller steps you can make these expansions, the more energy you're going to get. But it's going to asymptotically increase until it reaches a stopping point. There's a maximum amount of energy we can get. It won't go up in a straight line forever. So, one last one, and that enthalpy of the state functions for a reaction. Enthalpy is a state function for a very specific heat exchange under a constant external pressure. Enthalpy is different from internal energy and it's different from heat, and that by defining the path, you generate the state function. We say the energy produced when you heat something at a constant pressure. What that means is that it's an object that's done open to atmosphere. Because a gas is allowed to expand, change its volume, the pressure stays constant. Most reactions we will run are open to air, and so they will see a constant pressure rather than a constant volume. But considering that work done at a constant pressure is force over our area, and volume is area times distance. So work being force times distance, is we get the work at a constant pressure is negative P delta V that you saw. The negative sign is just there to show that exogonic, the work being produced, gets negative sign. So with that in mind, internal energy can now go from Q plus W to delta H minus P delta V when you calculate this at a constant pressure. But essentially, what is an explosion? Explosion is the production of gratuitous amounts of heat and a rapid expansion of gases under constant external pressure. The measurement of energy of the explosion will just be a quantification of those two aspects. How much does the gases expand? How much heat is produced? And the cars work based on that function. This is the last one for this video. Okay, 101.3 joules per liter atmosphere. And delta H minus P delta V. So, what would the internal energy of the system be if it absorbs 123 kilojoules of heat and it's allowed to expand by volume of 58.94 liters under external pressure of 3 atmospheres? So with that in mind, finishing this off, okay, this is already given. So we have the delta U equals positive 123 kilojoules. And then minus your pressure, which is 3 atmospheres, times your change in volume, which is 58.94 liters. The only problem here is that liters, atmospheres are not equal to a joule. So I have to do a little conversion real quick. So 101.3 joules in 1 liter atmosphere. And in 1 kilojoule, there is 1,000 joules. So with that in mind, negative 3 times 58.94 times 101.3 divided by 1,000. That's negative 17.91. 123. So, all said and done, the total amount of energy is increased by 105.1 kilojoules. And that's where we're stopping. Tomorrow, next video we will look at involves the specific heat capacity of objects.